So my name is William. Today we're going to be talking about the Fourier transform, the FFT, and how to use it. My original goal for this talk was I was going to take this whirlwind tour through a bunch of digital filtering techniques. And then as I was putting that together, I realized that it was probably a better plan to instead try and give you a thorough and deep intuition for what the Fourier transform is doing and why in the world you would and how you would use it. So this is a bit of an experiment for me. This is the lecture that I wish I had when I was an undergraduate in electrical engineering. So please let me know the things that don't make sense and things that I can improve. So ultimately, this talk is the story of a moving point. And this point is moving in one dimension, the horizontal dimension. And it's moving left to right. Time is increasing infinitely, but the function that returns to the position of this point on the horizontal axis causes it to oscillate. This is a periodic function, and in fact, this is the cosine function. The position of the point on the x-axis in Cartesian coordinates, so the horizontal axis is the cosine of the time. But this particular point was not content to exist in one dimension only. No, it wanted to move in two dimensions. But these two dimensions are independent. So just like the previous slide, this point, which is moving in two dimensions, is oscillating back and forth on the horizontal dimension, but is also oscillating up and down on the vertical dimension. So the vertical position is described by the sine function, and the horizontal position is described by the cosine function. As you can see in red, I'm drawing out the sine function over time, the vertical position, and the cosine function is drawing out the horizontal position in green. So the takeaway from that is that the sine and cosine give you a circular motion. And the sine and the cosine is described here, the vertical and horizontal dimensions. And since mathematicians like to complicate things, we have special names for those axes. The horizontal axis is usually called the real axis, and the vertical one is called imaginary. It's not imaginary. It is called that sometimes. So if you see that term, don't be afraid. So when we talk about points moving around a circle, it's important to also consider the notion of rotation and time and speed of rotation. So when we talk about speed of something, we talk about the distance it travels over a period of time. So in this case, a point that moves all the way around a circle is moving around one circumference. Now, if you think back to your geometry, you remember that one circumference is equal to 2 times pi times the radius. And there's a nice little animation in the bottom left by fabulous animator Lucas VB, you should check him out, illustrating that idea that a radius times 2 times pi is the circumference of this circle. So when we also talk about distance, that's the distance the point has moved around the circle, we want to talk about time. And the time, for reasons of convenience, let's just consider the distance it moves in 1 second. So up here we're talking about circumference in 1 second is the same thing as 2 times pi times the radius in 1 second. Now, we had seconds in the denominator, the lower half. And because that happens often, 1 over seconds, we give that a special name. And that name is hertz. And it's a unit of frequency, of oscillating motion. So really, if you want to intuit this, you should think of a clock. Clock has hands that are rotating around the face of this circle. And those hands rotate at different speeds. They're traveling the same distance, but they're doing it in a different period of time. The hour hand, for instance, is moving 2 times pi times the radius, but it takes 360 seconds to do it, which 1 over 300, or 3600, and the top right is 2 pi, 2 times 7 to the negative 4. And then the minute hand travels that same distance, the radius, or the circumference of the circle, 2 times pi times the radius of that circle. It does it in 60 seconds. And the second hand, again, is moving around the face of this clock, is traveling around the circle, but it does so in 1 second. And illustrated here in the bottom right is, again, points rotating around the circle at different speeds or different frequencies. The top left circle is this lowest frequency, and it increases down to the bottom right. Okay? So keep this thought in your mind, the notion of points rotating around circles. the notions of clock hands moving around. And now let's talk about our data. So we have a time series of measured data. This is anything that you measure. This is your heart rate over time. This is the height of tides over a year. This is the energy on an antenna on your cell phone. This is anything that you measure at fixed intervals in time. And you take those measurements and you save it digitally, so now you have an array of measurements. So the point here is that data is discrete. You have discrete individual measurements measured at fixed intervals. And since you know that interval, you know how fast you made your measurements, every second, every day, every hundredth of seconds. That time is what we're calling T sub s. Because again, it's 1 over seconds, we can also call that in hertz. So it's just 1 over that time period. Okay, so here's where it gets interesting. This data here is in 1 dimensions. It's a measurement over time. But we look at the data and we say, there's something interesting about it. When we measure data, maybe we take the mean or the variance, or you look at the distribution, you look at a histogram, or if we have an image, you look at the red and green and blue channels. These are different ways that you can look at your data to intuit what's underlying. But when you have data that's periodic, or you think it might be periodic, one of the ways to look at that data is to look at the frequency content. What is the underlying periodic nature of your data? And to do that, we're going to transform this one-dimensional data into 2 dimensions. And we do that by projecting the data onto these circles, these moving clocks. So what you're looking at in the top is that same measured data, the same waveform of measurements. And if you can see the little red dot is traveling along, that's indicating 1 moment in time. And at that 1 moment in time, I am changing the length of the clock hand, as it were, on these lower plots. So the point is rotating around the circle in each of these 3 bottom plots at the same rate. But for each measurement, I'm changing how long the clock arm is, so to speak. Okay? So you can see that when the measurement is very high, the clock arm is long. When the measurement is near 0, the clock arm is at the very center of the graph. And in fact, when the measurement is negative, the clock hand switches directions. But the important thing to look at here is that we've taken our measured data and we have what we call projecting that information now into 2 dimensions. The 2 dimensions are these clock faces. And you can think back to the first slide we looked at. We have these circles, which we can also look at in independent vertical and horizontal dimensions. Okay? So this is looking at time instant by time instance. What if we took all of our measured data at once and drew it all in 2 dimensions? So essentially, what if we took our signal and we coiled it around that circle? Our 1-dimensional data now becomes 2-dimensional. We now have translated time into a spatial dimension. So again, as time passes, the clock hand ticks along the face of the circle, and our measurements are used to modulate the length of the clock hand. So what you're looking at here is, again, all of the measurements drawn on that face of that circle at one point. We're essentially wrapping around the circle. And as we increase the frequency, in other words, as we increase the rate at which the clock hand ticks around the face of the circle, it becomes faster and faster, and it spreads the data around that clock face. Essentially, it's coiling it up tighter. And you can see it creates some interesting patterns there. So now we have a bunch of measurements in 2 dimensions. We've taken all the measured data, we've coiled it around this clock face for a specific frequency. So every point in our measurement now lives in these 2 dimensions. We call this a vector. It's a line. And we can add these vectors together. So in other words, we're going to take all of our measured points, project them into 2 dimensions, and then we're going to sum all the vectors together. So a quick aside, in summing vectors, we sum their components independently. So if you have a vector A and a vector B, their horizontal components will cancel each other out, and their vertical components will sum together. So in other words, vectors that are closer together sum to be larger vectors, sort of intuitively. Okay? And then the other point that we should make about vectors is that we could describe them as having a horizontal and a vertical component, or we could describe them by their length and the angle at which they make with this, the zero, the horizontal axis point. Okay? Tracking with me so far? Okay. So this is the same picture here, where we're taking our measured data, we're wrapping it around the circle, and each frame of this animation, we're wrapping it around a circle of an increasing frequency, a faster rate of rotation, as it were. And what we're doing for each frame in this animation, we're taking all these points that live in 2 dimensions, and we're summing them together. We're taking the average, essentially. So you could think of it like finding the center of mass of this shape. So all the vectors summed together give us one vector, and that one vector, we can look at the length. So the one vector, the average vector of this shape is shown up in the top right. And then if we just look at the length of the vector, that's what we're plotting in the bottom right. Okay? And you can see that something magical happens right about 1.1. The shape all aligns such that most of the points are close together in one area of the graph, which means that when you sum all those vectors together, it becomes very large. So we call that a Fourier transform, effectively. We're looking at the length of the vector, we're projecting all of our data onto some frequency component, and we're looking at the periodic nature of our data. Because as time is progressing, we're positioning the data such that at a specific frequency, it all lines up on top of each other. Okay? So what if we looked at a different signal? This is some data that I created. I added some noise to it. We look at it and we think, there's probably something periodic under there. It might be hard to figure that out if I was just to sort of count between the peaks. So instead, we're going to do the same process that we've already done. We're going to take our measured data. We're going to wrap it around a circle that's traveling, a clock face that's traveling at different rates. And you can see that coming up, when the frequency reaches about 2.2 hertz, all of the points line up. Wait for it. You see right about now, the vector is going to get very large because all of the data lines up on one side. The center of mass, the average of all the vectors, becomes very large in that one direction, meaning that the underlying frequency of how fast that clock is tracking caused all of our data to line up together and exposes this underlying periodic value of that data. And as it is, as it were, I generated this data by taking a sine wave of 2.2 hertz and manipulating a little bit. And you will see that at 4.4 hertz, we get a similar sort of peak, slightly less power. So even multiple of that frequency, because half the data in that instance lined up together. So really, that's the foundation. That's all that's happening when you take this discrete Fourier transform, or the FFT, and all this abstractions of integrals and complex numbers overly complicates matters unless you really need to worry about it. So as an aside, Leonard Euler, I think he's come up 3 times today in the sessions I've been. He got around. He was, chilling one day and playing with some math, and he made a discovery. And that discovery is useful but complicates your lives because he figured out that if you took a sine of some value and you added it to j, which is the square root of -1, and you multiply that times cosine of the value, that amazingly equaled e raised to the power of j times the value. It's pretty astounding that that works out. But effectively, all that means is he came up with a shorthand way of expressing this sine and cosine, this circle information, into e raised to the power. And because of this, it's shorthand notation. It's used almost everywhere when you're discussing these Fourier transforms. So when you see e, j, something, just think in your mind, take a deep breath. Oh, it's a circle. And we'll see that come up a little bit. So everything that we've talked about up to this point, we can express mathematically as a summation. Remember, we're summing all our points. And we're taking our points and we're mapping it onto these circles. So up at the top, it's an equation. Big X is our output, what we're looking for. It's the frequency information of our signal. F sub k is the specific frequency we're interested in. We probably want to look at a whole range of them. And we're taking our data, which is x, shown in red, and we're multiplying it by exp, or e, times j times something, which is the circles. So we're multiplying our data times circles of varying frequencies, and we're summing them together, and then we're shoving it into an array, x, big X. And again, if you were to get rid of the exponential value and break it out so that it's more intuitive, you can say, well, right, the horizontal values of this output, that's the summation of our data times the cosine. And then the vertical, what we call imaginary, that's the summation of our data times the sine function. And these equations just describe what we looked at pictorially, taking our data, mapping it to a circle, summing all the points, and then looking at the length of the vector. So in a block diagram, what we're doing is we, again, measure the data. We pick a frequency, 1. We arrange our points around a clock traveling at 1 hertz. We average all the points. Now we have a vector, an average vector, and we look at the length of that average vector, and we save that measurement. You could also look at the angle of that vector. For 95% of what you would ever want to do, you really don't care about the angle, but it's there. We call that the phase. And then you repeat this process for every frequency that you care about analyzing. So a few notes, a few gotchas. If you'll notice, in that mathematical equation, the sample rate, how fast we took our measurements, never explicitly appears. It turns out it doesn't matter. Whether or not you're measuring your heart rate every second or the tide every day, when you put it into your computer, you're putting it into an array of fixed measurements at fixed intervals. All that you would end up using the sample time for is at the end of the day when you're doing your analysis, when you're showing it to your boss or you're trying to figure out what's going on, you normalize the values to figure out actually what the frequency in whatever units you care about, whether it's days or seconds or hours. Another important note is there's no point in measuring frequencies that are greater than 1/2 your sampling frequency. Now that's a little crazy. If you spend some time looking at the geometric graphs we were showing, you can probably convince yourself that that's true. But just know that. And finally, again, I'm reiterating this point. All that we're doing is for each frequency, we're summing all the measured points projected onto this circle. And down in the bottom that's how you will normally see this discrete Fourier transform written out. So summation, data times circles. So if you were to write this out as a computer program, I call this pseudocode. I think it's actually valid Python. So how we would write this out, if we were going to create a computer program to compute the Fourier transform and measure data, we would iterate through all our frequencies, for frequency and frequencies. Frequencies is an array of 1 through 100 hertz, for instance. Then we would iterate through every one of our measurements. That's 4 measurements in our measurements. And then fractional distance is just tracking where we map those points to around the clock face, because we're spreading them evenly around the clock face. And the average point, again, is the summation. So for each measurement, we're summing them all together, where we're summing our measurement times e to the 2 pi frequency fractional distance, which is mapping the point to the circle. So we have an accumulator, and we append the average value into our Fourier transform array. Great. So this works. You can do it. You can copy the code in whatever language you want and try it out. You'll notice, though, that this is not a terribly efficient algorithm. You have a nested for loop. It's actually n squared efficiency. So you're iterating over every frequency and every measurement, and generally those two are going to be on the same order of magnitude. So for most of history, this was not a terribly easy thing to do, until these two guys showed up, Tukey and Cooley. And they came up with the fast Fourier transform algorithm. I believe this was in the 60s. I don't know the actual date of the paper. I think I have a link in the slides. And they took that algorithm that we showed on the previous slide, and they reduced it to n log n computational complexity, which is tractable. And as a result of doing that, of publishing that paper, they've changed everything about our modern world. All of our digital electronics, our music players, our podcasts, our cell phones depend on taking lots and lots and lots of these Fourier transforms and doing it very rapidly. And if it wasn't for their paper, that would never have happened. So those two guys, pretty fly. Okay, practically speaking, any language you have, you will be able to find an FFT, a fast Fourier transform package. One of the more popular ones is written in C. It's called FFTW, fastest Fourier transform in the West. And most languages will just wrap over that, and it is very fast. And if you were going to use that, all you need to know is that you have a function, and you pass to the function A your data and the number of bins you want to calculate. Now, that word bins you'll see commonly used, and that just means, like with a histogram, you have to choose the spacing of measurements to make. Because the frequency components are not discrete, you have to choose at which interval. Do I want to measure 1 hertz, 2 hertz, 3 hertz, or 10 hertz, 20 hertz, 30 hertz? And the number of bins chooses that granularity. Okay? So you pass in the data and the number of bins to this algorithm, and it spits out an array of the Fourier transform, where k, the length of the array, goes from 0 up to the number of bins you chose. And like I mentioned in a previous slide, you only care about the first half of that. Yeah. So you take the first half of that data, and that's your output, your frequency information output. Now, that output is two-dimensional. And we represent those two dimensions as complex numbers, real and imaginary components, horizontal and vertical components. And remember, what we really care about at the end of the day for almost everything you want to do is the length of the vector. And you do that by taking the absolute value. So you shove in your data, shove in the number of bins, spits out a complex array. You take the first half, take the absolute value, and you're golden. Okay. But, like I said, the output doesn't actually correspond to physical numbers. You have to plot it such that it's understandable. So the common question you get a lot is, well, okay, I got an output array, and I got the absolute value, and I see powers, but what are those actual frequencies? So the output frequencies are just 0 up to the sampling rate in hertz. You're looking at the first half of that, so every bin is corresponding to 0 up to fs over 2. Okay, so if you're going to write it out in Python, it would be this frequency axis array. Another practical consideration is how many bins do you choose? So here's an animation of, again, the signal up top. I'm passing it through this FFT algorithm, and I'm plotting it. And I'm changing the number of bins. So that's what plotted at the top of the animation. I'm going from 10 bin or 30 bins all the way up to, I think, 256. So you can see some interesting patterns emerge. You'll also notice past a certain point, we didn't really gain much. You also notice below a certain point, you don't get much information back. So practically, you want to play with that number, modulate the number of bins to see if visually or whatever algorithm you're building on top can actually use that information. But in general, the number of bins you choose is around the same order as the length of the data you have. And you can also change the number of bins based off the speed of the computer you have. If you're computing this on an Arduino, probably want a limited number of bins. If you're computing this on your laptop, go to town. So that's the practical use point number 1. Practical use point number 2 is windowing functions. I worked at a defense contractor with a lot of experienced engineers, and I got this question a lot. They would come by and they'd say, hey, I'm taking an FFT, and I'm supposed to take a windowing function. What does that mean? And all that's happening is that for reasons that probably don't matter practically to you, is that you have your measured data, and the windowing function just modulates or reduces the power at the beginning and the end. It's a function that you multiply times the data, and that's shown in green. So if we have 600 measurements, I multiply that green function times our measurements so that the data at the beginning and the data at the end is sort of reduced and ignored. And when you do that, you get much prettier outputs. So shown up top is, again, our measured data, multiplied by this green windowing function, and at the bottom is the Fourier transform output. And you can see that as I impose this windowing function, I get better resolution between the low points in my graph, that's the noise, and the high points, which are the actual frequencies that make up my data. So the takeaway here is use a windowing function. There are a multitude of them. You can probably just choose one of them, and it will work equally well. If you really want to try things out, try different ones and see how it looks. But use a windowing function. That was point 2. Point 3, if you have a lot of data, or you have data that's constantly running, say you're recording a microphone, and you want to look at the frequency output, you're going to have to set up some process to pull in data, compute the FFT and plot it, and then pull in some more data. And generally what is done is you take a chunk of data, use that to compute the FFT, then take the next chunk of data and overlap some of it, such that the latter half of the data in the first window becomes the first part of the data in the second window, and so forth. So you have overlapping windows of data that you use to compute your outputs. And generally, that overlapping window is about 50%. So half of the old data becomes the new data. Okay? So, wrapping things up here, I have a canonical example of the Fourier transform where we look at some audio information. So I'm going to play this clip. This is me plucking some guitar strings. So I recorded this on the laptop, and I pulled it into Python. So a string of measurements. And then I took those measurements, and I chunked them into windows and computed the FFT, and I'm plotting those on this next graph. And this is what we call a spectrogram. The spectrogram is showing frequency on the x-axis, time on the horizontal axis, and the colors represent the power, the amount of energy at various frequencies. And you can see that at the beginning of the audio clip, there was silence, tracking up from the top left down, silence. So the output is sort of uniform. And eventually, at maybe 15 seconds in, I pluck the first guitar string, and you see a strong component at 15 hertz. Now notice that the output I plotted here is in bins. This is the direct output for the algorithm. I can look at the sampling rate of my sound card, which is probably 44 kilohertz, and I can use that to change how the bins are plotted. So you can see that I hit the first string about 15 seconds in. I hit it again at 20 or 30 seconds, and you can see the power level increases across the board. I hit it again at 43 seconds, 60 seconds, and then at about 70 seconds in, I plucked the next string up. So I went from a E to a, whatever the next string is, G. A. Play the mandolin, not the guitar. And you can see that the frequency, the fundamental, the lowest one, increased. It was a higher note. You also notice that the original sound energy is sort of bleeding through because the string is still resonating, so we see that component. And you'll notice that the purple illustrating the highest power, sort of fades in intensity as I get to the bottom because that vibration is diminishing. And you also notice that not only do we have a single tone, shown here on the far left, we have multiple tones. And that's what gives the guitar its guitar sound, is the intensity of all these tonals. And you'll see that the higher frequency tones tend to diminish faster than the lower frequency tones. So, final notes. If you look at the output of a Fourier transform, most of the time the y-axis will be plotted logarithmically. It's usually an easier way to view powers. So each tick, instead of being 1, 2, 3, 4, 5, will be 10, 100, 1,000, 10,000. So as a consequence of that, when you're looking at Fourier transform plots, outputs of frequency, and you see small variations in power, if it's plotted logarithmically, those are actually very large variations in power. So the previous plot was, again, logarithmically scaled, so there were quite large variations in what the sound card was picking up. Okay, point 2 is pretty interesting, and I'm sorry that we don't have time to go into it more, but the inverse Fourier transform works just like the Fourier transform. So not only can you take time series data and transform it into a frequency domain, you can take frequency domain information and transform it into time series data. So you could take measured data, take the FFT, fiddle with the frequencies, and then take the inverse FFT, and now you have data that's been filtered some way. Should play around with that. Take your FFT, delete the middle part, and then take the inverse FFT, which works just the same way. Most languages, you have an FFT function and an IFFT function. And just see what the output looks like. And a final point here is usually you'll get better performance if you take your signal and remove the average. The average just scales the whole plot up and down. If you remove the average, the scaling works out much nicer. So in summary, again, measured data, mapping it onto a basis function, and the basis function is a circle, a point rotating around at different frequencies. We take the two-dimensional average of all those points mapped onto that function. We find the magnitude of the vector, how long that vector is, and we save that. And the FFT algorithm is an efficient algorithm we use to compute all those values. And it gives you a vector of signal averages at various frequencies. So I wrote down some cool ideas of, what would we want to do with all this if we had time to play around with experiments. So the first one is, if you watch the 5th episode of the first season of MacGyver, he's breaking into the bad guy's house. The bad guy has a safe, and the safe is activated not by punch code, no, it's activated by tones. So MacGyver listens to the tones, and he pours out wine glasses, and he emulates the tones and unlocks the safe. It's a great scene. I wish I had a clip of it, because I busted out laughing the first time I saw it. Amazon Prime has it. Go watch it. Anyways, you should make a safe like that. Terrible idea, but it'd be a fun project. Maybe you would want to take the peaks, the highest values of your FFT, and train a machine learning model to recognize your voice or your cat's meow. The app, Shazam or SoundHound, uses this method to figure out what song you're listening to. It records the audio, takes the FFT, and looks at the peaks, and then matches it to a library because the frequency information of the songs match up. You can take the FFT of an image. You take the horizontal FFT and then the vertical, or the other way around. And you can look at frequency content of a two-dimensional image that way. You can measure if your house really has 60 hertz power, or if your power company is messing up. You could measure the voltage, take the FFT of the voltage. You could take the FFT of stock prices, Apple price over time, and see if there's periodic components. Obviously, the trading floor is closed on Saturday and Sunday, so you would probably see a very strong 7-day frequency component there. Maybe you want to measure your energy or your sleep patterns. That's what I've been doing over the past year to look at how my sleep affects my energy and to see if there are patterns in there. And then for a fun app, you should check out the acoustic picture transmitter on iOS. I have it on my phone. You'll take a picture, it'll take the picture, compute the audio, the time series audio that corresponds to the picture. So on your phone, I can transmit a picture, and you look at the spectrogram, and you see the image in the spectrogram. It's pretty wacky. So closing things out, thank you for your time. Here are some helpful resources that if you're still scratching your head, these will give you different pictures of what I'm talking about. Really just iterate on this. It takes a lot of time to let it sink in of what's actually happening, but when it does, it'll click. And these are 3 great links here. You can ask me questions afterwards or on Twitter at Galamine. The slides and the code I used to generate this presentation I will be putting on my website. And thank you for your time.